Ready, set, go. Introduce.
Ladies and gentlemen, we have tonight Ken Bertin, a very long-time member of the club, who served as president for 2 terms and first vice president for 2 terms, and has helped with coordinating snacks and arranging discussion groups and generally making the club run for a couple decades now. So he will have assistants from throughout the audience, you know who you are, to share the biggest news stories of last year with us. So without further ado, I give you In the News 2017, the greatest hits.
18.
2018, yeah, this is 19.
Okay, I just wanted to tell you something. We changed the format of this just slightly, or I did anyway, to where there's a lot of subject matter going on. So it wasn't necessarily the top stories of the year. It was more about the objects that were really studied in intensity. So, like, for example, Bob's going to do things on solar, and Dale's going to do Mars, and Jeff is going to do Jupiter, and Diane, of course, is going to do all the satellites, or many of the things that we're using, concentrated on that. And Jerry, of course, is going to do a little bit more about LIGO. Did I do it right that time?
Yeah.
Okay, I'm glad. All right. So, and if you have any questions about this, this is kind of time controlled. We're trying to keep everybody to about 10 minutes, except for Jerry, who's shorter subject, 25. And whatever they can give back to us, we'll be able to give back to them. Of course, I didn't say Angelo. Angelo's got to do this outer space stuff. Sorry about that. He's going to do much of that has to do with, which is not inter-solar system. The reason we use solar systems so much is because it's really an interesting thing for study, and that's what we're going to do. So there we go. Without further ado, I will introduce our first speaker. Our first speaker will be Dale Partin, Dr. Dale Partin, and Dale will be discussing Mars. You are on your way.
How come it's not advancing, Ken?
Because you got to do it in the middle of the top.
Did it in the middle.
No,
Oh,
here.
your top.
Yeah, there you go. How about that?
Okay. When Ken first talked to me about this, he asked me to put some emphasis on the close approach that we had with Mars in the middle of last year. So that's what I'm going to do. Various aspects of that. It's not like they get this close, right? I think everybody understands that. Come on. Why?
You gave me all 4 of them, that's why.
End of July last year, Mars went from looking this big in May to this big. It was 24 arc seconds in diameter. Some of us will remember back in 2003 when it was closer than it had been in forever, and it was only a little bit bigger back then. Back then, 2003, there was a massive dust storm. Everybody was thinking that we'd get such a wonderful, clear view of Mars, and Mars just, clouded up on us with dust. And something similar happened heading up to this close approach. These are a couple of pictures on the surface of Mars taken by the Curiosity rover, showing things going from bad to worse, and then it got worse. And the fact that we saw this the last time Mars was super close makes me wonder if that's because it wasn't just super close to the Earth, but super close to the sun. Maybe extra heat from the sun just barely tripped it into the planet-wide dust storm. I don't know, I just wonder. But if you're down on the surface at Curiosity's position, looking up at the sun, it sort of got real dark. It makes you think that if you were living in a colony on Mars, you you would not want your electrical power to be dependent on sunlight. Because if one of these things happened, you'd be dead. So, as we got close to Mars, Mars went into what's called, so Mars approached opposition, where it's exactly on the opposite side of the sky from the sun. And that means it was in retrograde motion. Each night, if you looked at Mars at the same time of night, you would see it move a little bit farther to the west. But if you take pictures each night and keep the background of stars fixed in the picture, then Mars appears to move from west to east across the background of stars because of its orbit around the sun. Except it does this weird thing. It's going from west to east, and then it turns around and goes back, and then does this again. And that's a well-known phenomenon due to the fact that the Earth is moving a lot faster than Mars is in its path around the sun. So here's where Earth is catching up to Mars and passing it. And so from the moving perspective of our planet, Mars appears to reverse direction. But a lot of people get worried about retrograde motion. I mean, I did a little searching. You know, it can have personal implications. Did you have a problem?
Wow.
Let me tell you how serious this is for some people. Gee, I feel like I'm getting a little pink here. I worked with a guy in the auto industry doing research, and he had a doctorate in electrical engineering. And he asked me for permission to go to an engineering conference in his specialty that was held out west somewhere. And so I said, well, I'm sure I can get you approved to go. Give me a few days to get some signatures, and then you can make your reservations. And the company would pay for everything. So, you know, I got approval after a few days. I go back and I said, okay, you're good to go. You can make your reservations. He says, I don't want to go. I said, wait a minute. You said you wanted to go. I got everybody signed off. Go ahead. He says, I don't want to go. I said, why not? He said, well, the conference, it was going to be like 3 or 4 months in the future. He said during the conference, he checked, and Saturn would be in retrograde motion. I said, you're serious. And he was really into that kind of stuff. And he said, yeah. I said, okay, don't go.
You're fine.
Yeah. Well, I can't say anything negative because that's probably something like religious harassment if I do, you know? I mean, right? So other things are going, I mean, there's all kind of things that are correlated with Mars being in opposition, one of which is that's when you want to send spacecraft to Mars. And NASA, because it's closer, right? So NASA sent a spacecraft to Mars, and at the next opposition, it's planning to send another one similar to Curiosity, but with more biology-related experiments on board. But this time, it was called the InSight lander, and it landed successfully. People were kind of happy about that. So I'd like to just briefly talk about what's on that lander. Here's a picture of it before it was launched, just to give you an idea of the size of it compared to people. These are solar cells to generate energy for the lander. Here's a sort of a schematic, well, a simulated drawing of it operating on Mars, showing its various parts. And I'm going to just walk you through real briefly what the main three instruments are. There's this thing. They have a little crane that's set down on the surface. That's just the cover of it that you see there. And it's a French instrument. This thing is an ultra sensitive seismometer used to measure Mars quakes. This is the instrument that kept them from launching 2 years ago. It has a super good vacuum inside, and they detected a tiny leak, and they couldn't get it fixed fast enough, so they had to delay till the next time Mars was in opposition to launch the thing, at a cost of another $200 million, by the way. You know, what they're thinking is, if there are any plate tectonics, which there probably are not, on Mars, they would certainly pick up anything from that. But the more likely thing is small meteorites coming in and hitting Mars. Probably, unless they come straight down, they're pretty big, just creating a shock wave in the Martian atmosphere that hits the ground. And they'll be listening and picking up any vibrations bouncing around in Mars to learn about the internal structure of Mars. Major questions are how thick is the crust, how thick is the mantle, how thick is the core, and they might be able to figure out if the core is liquid or not. Another experiment, this one is German, has a pole that drills down into Mars. It's actually 16 feet long, and they have temperature sensors every 4 inches along its length. And the idea is they can learn something about how much heat is down on Mars by the temperature profile, as that heat diffuses up to the surface. And finally, this is a U.S. instrument that sends radio waves back and forth to Earth, and by measuring the Doppler shift with extreme precision, you can sense any non-uniformity in the orbit of Mars. Again, that would give another way to look at the internal structure of Mars. So those are three instruments. None of them is going to get us any information in a hurry. It's going to take a while. So be patient and be careful. Jupiter is going retrograde this summer.
Okay, our next presenter is, let's see, I knew that, is Bob Berta, and he's got solar, and we are 30 seconds behind, so here we go.
30 seconds.
Greetings. Tonight we're going to talk about one of my favorite recent probes, and this is a probe which is going to the sun, or going close to the sun. But this is actually very interesting to me because, you know, we look at the stars out there, but the closest star to us is our sun. And there's a lot of things that that sun can tell us about its effect on us, and also things about the Earth, as far as perhaps things that have happened to the Earth many times, many eons ago, when we had mass extinctions, etc. So it's going to be an interesting thing to study about this. There's two actual solar programs. One is the, excuse me, it's the, okay, but the Parker is the one from the U.S., the Parker Solar Probe, which is the main one I'm going to talk about, but also the European Space Agency also has one. It's called the Solar Orbiter. And these hopefully will resolve decades-old questions about the inner workings of our nearest star. The close-up study will have a lot of major implications as like the energy that comes from the sun, it powers the life on the Earth, but also how does that work? We're not really 100% certain how that works. It also, a big deal is it triggers the space weather. our sun, the energy it puts out can affect the Earth from weather, not only, what do you call it, the weather you're used to seeing, but actually as far as the weather from the sun affects our Earth satellites, electronic equipment, and so on and so forth. 150 years ago, we weren't really so much at risk of having problems caused by the sun, but now we are because of our satellites, electronic equipment, our power grid system. We're at the risk of things, and we want to learn more about it, how we can prevent major disruptions to our infrastructure. Okay, there's always one question: why won't the Parker Solar Probe melt? Well, we'll get into that in a little bit. And the thing is, we're not really going to go into the sun. We keep talking about this probe going to the sun. Well, it's not really going into the sun. The closest we're going to get is still about 4 million miles away from it. But that's still close enough to cause a lot of problems. But they have cutting-edge technology, and engineering will help it beat the heat, we hope. We'll see when it gets up there if it actually survives. It'll be a very, very lot of energy from that, a lot of heat. If the Earth was at one end of the yardstick and the sun on the other, the Parker Solar Probe will make it within about 4 inches of the solar surface. So we're not really, mileage-wise, that close to the sun, but it's enough to get very, very hot there. This is a 7-year mission. It's going to be probably, I think, 6 flybys. Not going to be just one flight. We're going to have, I think, 7 total loops coming around. And finally, the last one will come in within very close. I think that's when they get in within about 4 million miles of it. The probe itself, the Parker Solar Probe, is named after Eugene Parker, who was first theorized that the sun constantly sends out a flow of particles and energy called the solar wind. And he wanted to explore one of the last regions of the solar system to be visited by spacecraft. You think about it, we've sent spacecraft to other planets out, to the farthest reaches of our solar system, but we haven't really studied that much our closest neighbor, the sun. Big star, I should say our closest star. Okay. A couple of things that they want to solve are things like why in the corona of the sun, okay, it's 100 times hotter than the surface below. And that sort of doesn't make sense. If you have a fire there, for instance, the closer you get, the hotter it gets. Well, in this case, the farther you get away, the hotter it gets. And we really don't have a clear understanding of why that is. So we hope to understand that closer. Right now, they think that it's delivered by electronic waves called Alphen waves, I think that's the way you pronounce it. And they move outwards from the sun's surface. Other things that might be due to things which are, they call like nanoflares. They're like bomb-like explosions of material on the sun coming out, similar to prominences that we can see from the Earth through our telescopes, but much smaller, much more microscopic. So accumulation of these could be causing that. But either way, the Parker Solar Probe's measurements will directly measure this and see if we can figure out a little more why this mystery is there, why it's so hot away from the surface. We also want to find out what exactly accelerates the solar wind. The sun's constant outpouring of material that rushes out about 1 million miles per hour, which is about 1.6 million kilometers per hour, and fills the solar system far past Pluto. And I mentioned earlier, that can cause space weather when it reaches the Earth, triggering things like the aurora, which is pretty when we see it, satellite problems, which aren't so nice, and even in rare cases, power outages. In previous meetings, we've talked about the effects of some of these power outages. The big one back, I think it was called the Carrington event back in the 1800s, when a mass ejection, solar mass ejection, came out from the sun directly towards the Earth. And in those days, we didn't yet have a electrical system, distribution system that we now have, but they did have telegraph lines. Well, through the electromotive energy promoted from this, it actually energizes the lines at a much higher voltage, and they had, at the teletype operators, actually had fires would start on the operator's desk because of the spark caused by electricity going back through their teletype machine. Okay. Okay, the other thing we're going to do is measure the sun's particles, magnetic and electric fields, solar wind, and more. And Parker will provide insights on stars everywhere in the universe. So what we're learning about our own sun, we can extrapolate from that information about other stars in the solar system, excuse me, in the outer star system. Took a pretty big rocket to launch this. It was called the United Launch Alliance Delta IV Heavy Rocket, and that was, that's a satellite here. Okay, that's the satellite or the rocket taking off there. That was a rocket that was one of the heavier rockets, one of the heavier loads we've launched, as I believe. And it's also going to have a new record. It's probably going to be the fastest moving satellite ever. When it gets close to the sun, it will be actually traveling at 430,000 miles per hour. That will be the record for the fastest moving object made by humanity. So that's kind of cool. Okay. Let's see now. Okay, the groups that worked on this was the University of California, Berta, my old alma mater, the Naval Research Laboratory in Washington, the University of Michigan in Ann Arbor, my wife and my kids, well, some alma mater now their current college are going to, and Princeton University in New Jersey. And the thing I thought was really cool about it was I and my son, Brian, are going on that probe, you might say. Let me get this to work here. Okay. There we go. Okay. They had a program. I think I read that very well. But NASA put out word, if you wanted to go to the sun on the probe, fill out your name on an application. And they took all these people, put them on I guess a micro SD card, put it on that satellite. So I'm going to the sun, I'm going to burn up, probably there. So that's kind of cool. So hopefully it works. And if the mission fails, it was probably because of me, so blame me.
The Warren Astronomical Society is on that chip too.
Oh, that's right, they are too. Okay. And that was when you talked about the high speed they went on. Okay. I have one other thing I wanted to talk about. This was not the solar probe. This is a new telescope, and this is the excuse me, the 30 millimeter telescope. It's at the Hawaii Supreme Court authorized. The date they authorized it finally was October 31st of 2018, and this was put on sort of a rough road to hoe because the native Hawaiians said that's a sacred place up there and we don't want any more stuff up there. And really the reason it got the forward to go with it is because they could not provide any information that they're actually doing anything on the mountain, any religious ceremonies, any memorials or anything else on there. So the court that was hearing the suit, the Indians said, we don't want it there. It said, well, you're not using this mountain for anything that we can see, and therefore they let it go. And that was interesting because there's several other observatories. Kip Peak is another one that comes to mind that various people, Native Indians, Native Americans, have caused some problems because they say, well, that mountain is a sacred mountain or whatever. So we've had to deal with some other issues besides just getting the money to build the thing and building it. So for years, protesters, include a lot of environmentalists, said it would be a mistake to put that up there. But it finally got done, and Hawaii's Governor David Ige, I think it's pronounced I-G-E, Ige, thanked the top court, saying he thinks that the decision was fair. Okay. Mauna Kea already has 13 telescopes up there, and again, their claim was that activists say that the construction of those telescopes has interfered with cultural practices. So I'm not one to say that can't be done, but we got it done. It's ready to go. Okay. Next.
All right. Now we're 2 minutes behind, but it's okay.
Okay, it's a PC one?
You're good, you're good.
Okay.
We're great, we're okay, our next speaker is Angelo.
All right. Let's go back.
They got a couple of those.
When Ken asked me to do Interstellar, he sent me 16 items to go over.
To choose between.
I cut it in half. All right. So, I will do that. Beginning with black holes. The University of Texas did a study of black holes last year, and the results indicated that the magnetic field around these black holes are a lot weaker than they had anticipated. This is important because the magnetic fields trap and channel particles into the black hole. And so it's an indication of how fast these black holes grow, and gives us better insight into the dynamics of the black hole. All right, moving on. I just found out that Dr. Dunifer is going to do a really good talk on LIGO. So I'm going to pass on this particular one and move on to the next one. Okay, this one, the University of Alberta did another study on black holes, and what they discovered was that strong winds develop in the accretion belt of the black holes. And these winds can blow away as much as 80% of the material that would normally fall into the black hole. So anyway, this is interesting. Again, it relates to how fast these black holes can grow. By the way, this happens on stellar mass black holes, not the supermassive ones. So interesting discovery. Moving on. This relates to supermassive black holes. The University of Alberta up in Canada discovered that around the supermassive black hole in M77, they discovered a ring of dust in the shape of a torus for the first time. So this is something new that was discovered last year. Interesting aspect of this, if you were to view this supermassive black hole along the equatorial plane of that torus, it would come across as a radio galaxy. You get the image of a radio galaxy. If you take a polar view of that supermassive black hole, it would be a quasar. So this is what kind of stuff that they're discovering. This is ALMA, down at the Atacama millimeter array, I believe. Is that correct, Jerry?
Yeah.
All right, moving on. Okay, this is Hubble, never ceases to amaze. Hubble discovered the farthest star yet at a distance of 9 billion light years away. It's a supermassive, it's a blue star, and it imaged this blue star again at 9 billion light years using gravitational lensing. All right, interesting Hubble discovery. And it's amazing how well you can use gravitational lensing to see these things that, you know, almost back to where the Big Bang. Oops, what happened?
You're good.
Cool. Helium, another Hubble discovery, using spectral analysis, infrared spectral analysis. Hubble detected helium, the signature of helium, in the atmospheres of an exoplanet located 200 light years away in the constellation Virgo. Interesting, because now we're getting to a point where we can see these exoplanets and actually determine the composition of the atmospheres. All right. Keep moving on. A team of researchers from MIT, headed up by Alan Guth, you might have heard of him, verified, made measurements of two distant quasars and confirmed entanglement, quantum entanglement. So this is an amazing thing. It's the first time it's ever been done with such distant objects as quasar. For those of you who may not be totally familiar with entanglement, when you get two quantum particles, when they interact, they can become entangled, which means that making an observation on one particle will affect the quantum state of the other one instantaneously, even if the other one is on the other side of the universe. So this is the first time that it's been done with quasars, and So it's no longer just a theory, it's real.
And how do
How
they-
that happens, nobody knows. But it's real, it does. Einstein called it spooky action at a distance. Still spooky, still spooky.
It's amazing.
Anyway, okay,
I know, but I'm not telling.
I think my,
You did great.
I think my 10 minutes of sand is
You did
up.
great. You were super. We're back.
I just
we're back on
made
time.
up your time.
He gets the golden award for being the, right on that. Our next speaker will be our renowned president, Jeff Macleod, who will be working on Jupiter for us.
Yeah, all right. I only cut 3 slides out, so I better get to it. But I need my notes.
Go for it.
Actually, I probably don't need these. We've gone over this so much. So Juno in 2018, and to a lesser extent Jupiter. Jupiter's jet streams, unearthly. Research from the Juno spacecraft seems to indicate that the jet streams of Jupiter are much deeper than we thought they were. And the way that this measurement was done, so these are wind speeds, but that's just the best graphic I can give you guys. So as the Juno spacecraft does its close science approaches to Jupiter, if it speeds up, it means there's more gravity that's pulling it down. When you go down in orbit, you speed up. And so by carefully measuring how the gravity of Jupiter is changing, they can actually infer the mass carried in these jet streams. And so we know the width of them, so if they're heavier than they should be, they must be deeper. And so this seems to indicate that Jupiter's weather patterns go down about 3,000 kilometers. And so by comparison to Earth, who has weather at about like 10 kilometers, that's pretty impressive. Jupiter's beauty, more than skin deep. So I kept this in chronological order. So this is from March 15th. And a lot of papers came out like all at the same time. And one of them was that the underneath the jet streams, it seems that Jupiter is rotating as a solid body. And if that's true, the transition between moving jet stream and rigid body might explain the strong magnetic field of Jupiter. But the image here is from a different paper, and it shows Jupiter's northern polar region. So before Juno, little was known about Jupiter's polar region. Most of the spacecraft that we sent came through in an equatorial kind of path. And it turns out that Jupiter is hardly recognizable when you look top down on it. And so in the south, we have a polar cyclone surrounded by 5 smaller vortices. And this in the north, there's 1 surrounded by 8. And we'll do a little bit more on this later. But these cyclones range in size up to 4,600 kilometers and host wind speeds up to 220 miles per hour. And there are some beautiful images of this. March 21st, the Great Red Spot has been known to be dynamic and changing almost since it was first discovered, but it has been getting smaller for quite some time now, and researchers thought that as the storm gets smaller, the wind speeds would increase, kind of like an ice skater spinning. When you pull your arms in, you go faster, and that's not what they've actually seen. What ends up happening is the storm gets taller. And they said that this might also explain the richer color that we're seeing. So as the chemicals get lifted higher up into the Jupiter atmosphere, they experience more UV radiation and take on a deeper color. And I also just want to mention real quick, the image to the left from the 1890s, that is just a skewed view of the other image. They just stretched it to look like what it was supposed to be. That is not an image from 1890.
I was gonna say, that color film from 1890.
Yeah, and like you got it at just the right time where like Io was, yeah.
Yeah.
So hopefully this animation plays. We'll see what happens here.
Should start up. Is it moving yet? Give it a
No.
quick.
You might have to tap
Oh.
on the,
How do I go back?
Side swipe.
back. There you go. I don't know whether it's
can you
gonna run.
tap on the actual video?
No. If it's not gonna run, it's not gonna run.
It's not gonna run?
Yeah.
Okay, well this was supposed to be, so NASA made a flyby image that kind of goes all around these areas, and it illustrates the differences in these cyclones pretty well. it's kind of hard to see from that distance, but like the structure of this one is drastically different than this one. And so there's really interesting, I mean, if you're a meteorologist, this is like...
The reason that didn't work is because I took that from your PowerPoint, and it wouldn't do what Keynote did. If I'd have known that, I would have used it.
That's all right.
Okay.
And then the only other thing to note here is that the red color is cooler and the yellow colors are hotter, which also kind of corresponds to their height. As they get lofted higher, they cool down. So when you're actually in that, you can Google this. It has some really interesting topology. This next one, watch it start playing now. No, okay. So these are from May 9th and 18th, and these are just photos taken during the 12th science pass of Juno. And so in the image to the left, you can see an anticyclone affectionately called W.A.S. and the north temporal band, I believe that they're talking about this. And in this other image, this is Juno flying outbound in the south. And so the great red spot looks like it's in the north, and it looks absolutely massive, but this is like distortion. When you get like too close to a sphere, it kind of distorts the surface. But a really cool image of the great red spot and Jupiter's southern polar area. So this is a cool one. Lightning reveals where Jupiter stores its missing water. So when the Galilean probe descended into the Jovian atmosphere in '95, it didn't encounter as much water as they had expected there would be. And by looking at the lightning on Jupiter, they also found that it produced low-frequency waves and were kind of different from lightning here on Earth. And so there was a couple of explanations as to what might be going on, but Juno has revealed that the Jovian lightning is actually much similar to lightning here on Earth. It does produce the same high-frequency waves that we see, which indicates that the lightning is caused by water clouds. So where there's lightning, there's water. And they've observed that most of the water on Jupiter is in the northern hemisphere, and very little at the equator, and a little bit less in the South Pole. And there's all kinds of stuff about the convection currents that's making this happen, but basically you look at the lightning and you can infer the water there. So if they send another probe, they'll send it where they observe this lightning. Europa's oceans. Hopefully this one will play. I didn't do anything.
No, I didn't. Like I said, it came over from PowerPoint, and when it does that, we're not going to be able to do that.
It's not going to play?
No.
Okay, so...
Can you do interpretive?
Yes, I can. I can do so I'm the ocean, right? No. So this white is the brittle crust of the European surface, and then this red and yellow is kind of malleable, harder ice that makes up the bulk of the European crust, and then this is actually the liquid ocean. And so if this plays, you get all these interesting convection currents, and it actually will lift subsurface ocean to the surface, which we've observed. But the interesting thing is, based on this model, it takes a really long time, tens of thousands, if not millions of years. So the thing is if we, what's the Europa Express or something spacecraft that they're trying to send? So if it sniffs the water on Europa, it might not tell us much about the ocean now, but how it was 1 million years ago, or 10 million years ago. So take that for what it is. This is July 13th. The Aurora Mapper discovered a previously undiscovered volcano on Io's southern polar region. And basically the same reason that we were learning so much about the poles of Jupiter. Juno's in a polar orbit, so it's seeing things that we just haven't had a good vantage point to see before. The brighter colors here are hotter regions. I have no idea which one's the new one, but we said South Pole, so that's the new one right there. That one. Previously undiscovered. Amazing. This was probably the most interesting for me, but I'm an orbit guy, so 12 new moons of Jupiter. So Jupiter didn't have enough moons. People were starting to be like, 60 moons, whatever. It's now up to 79. So now people are back in, whoa, that's a lot of moons. So these were discovered in the spring of 2017, but all of this stuff takes quite a bit of time to nail down, so that's why it's a 2018 story. And they were actually foolishly looking for Planet 9 when they found these. Jupiter just happened to be pretty close to the target area they were looking in, and so instead of finding Planet 9, they found 12 new moons of Jupiter. And 9 of these are in a distant retrograde group, which is actually subdivided into 3 distinct groups of retrograde moons, which are thought to have come from larger moons that have disintegrated through collisions but stayed in these groupings. 2 of the other moons are in this prograde group that's closer in and pretty normal, but the really interesting one is this Valentino, named for the great-granddaughter of Jupiter. And the interesting thing about this one is it is, oh, you're going to try to show that?
I can do that. Go ahead.
So it's a prograde moon, but it's crossing the orbit of the retrogrades. And there's nothing else like this anywhere else in the solar system. We've never seen anything like this. And it, it's thought to not be very stable, like it's going to hit something eventually. And the other interesting thing about this one is it's the smallest moon. It's like 1 kilometer in size. So very small. All right, there's all this like subsurface little particulates of ice welling up to the surface, and you can see 10, 100, 200, 300, 400,000 years, and it's still not quite to the surface. It's like 500,000 years for this stuff to get to the surface.
It's not bad.
It's not bad.
Don't rush it, Jeff.
I want it now. So I don't know. New moons of Jupiter. That's pretty neat. And this is a pretty good graphic, but if you've ever like gone on, I think Eyes on the Solar System does a pretty good job. Universe Sandbox does a pretty good job. There's like Jupiter, the Galilean moons, and then an absolute cluster, just madhouse of small moons. A lot of captured asteroids and just junk. I don't know how much it's really in this like nice flat disk. There's a lot of highly inclinated moons as well. Some cool
Looks like
stuff.
a lot of those orbital tracks cross each other.
They look like that, but orbits, there's a lot of space out there. I mean, these are really far out. Some of these moons of Jupiter are almost as far away from Jupiter as Mercury is from, I mean, they're really far out. They're crazy.
I wouldn't want there to be any debris in Jupiter's orbit that would kick it out of the
We have a
planet.
time
Oh,
factor.
yeah. Okay, so I'm gonna skip this one since we're low on time, but basically there's a thing called chorus waves. I had no idea these things existed, but they're called chorus waves because they sound like birds chirping and fires crackling, but they're high energy particles that can damage spacecraft, and it turns out that they are 1,000,000 times more powerful around Ganymede and about 100 times more powerful around Europa than like the background of like Jupiter. But Jupiter itself, these moons sit inside the magnetic field of Jupiter, and that's about 20,000 times more powerful than the Earth. So it's already 20,000 times, and then somehow it's getting another boost. And so there's a lot of research that needs to be done about that. Another interesting one. I don't know how much weight you want to put into this mathematical modeling kind of stuff, but data collected from meteorites seems to indicate that Jupiter had a growth disorder. Not that kind of growth disorder, actually a slowing down of its growth. So the new model has like 3 distinct phases where the first 1,000,000 years of Jupiter's accretion was really rapid growth of centimeter-sized pebbles in the early solar system. And then the next 2,000,000 years is a slower accretion of kilometer-sized planetesimals. And apparently, when it would absorb these planetesimals, it kicks out a lot of heat, and that heat would actually slow down the ability for Jupiter to accrete gas. So that kind of slowed it down for a bit, and then once it got to about 50 Earth masses, the final phase of accretion took over, and you get rapid gas accretion, and we end with a Jupiter with 300 Earth masses. So, once again, I trust math, but they can be wrong sometimes. We'll see what happens. I'm sure that model will be revised. Mysterious cold spot around Europa. So at the bottom here, this is the first full thermal map of Europa ever made, and they found a gigantic cold spot about 300 kilometers across, and they have no idea what's causing this. Okay, so there's different explanations. It could be thicker ice. It could be that the ice has a different composition. More to come. We just really don't know. It's still in the very preliminary stages. And Jupiter's moon Europa might have these crazy, they're called pennatites. Do you know, is that what it's pronounced as?
Spikes.
Spikes, penna spikes. This is an actual image of some desert in like South America, I would guess. But on Europa, they could last much longer, and because Europa is colder and drier than any desert on the Earth, they could grow much taller, about 15 meters in height, which could pose problem for a spacecraft trying to land there. Avoid the belt of these things. So the last two slides are just really cool images. So just take that in for a second. I don't know of any painter ever to have lived that has done anything quite as stunning as that. So good luck to you. And then this is Jupiter's north equatorial belt, and this is one of the closest images they've taken. So that is Jupiter in a nutshell, and I will see you guys next year.
Okay. All right, Diane is coming up next. And you're on your way. Push it as it is.
Right. Okay, so in terms of spacecraft, we saw the end of 2 venerable NASA missions and the launch of another.
Go ahead.
Okay, so NASA's Dawn probe had a little problem. It was running out of hydrazine. So Dawn had been up there for 11 years. It had visited not just a flyby like New Horizons, but actually orbiting 2 bodies in the solar system, which is unprecedented. First Vesta, and then Ceres, the 2 asteroids that account for about 45% of the mass in the main asteroid belt. The mission was marked by really cool photographs, amazing engineering feats, because traveling to, inserting into orbit, leaving orbit, and getting into orbit around something else is incredibly difficult, in fact, unprecedented. And a wealth of information that kind of caused us to rethink our view of the asteroids. You've got Vesta with its violent, molten history, and you've got Ceres, which turned out to be cool, watery, perhaps, and quite a fascinating place by itself. So in fact, one of the stories that broke last year was that Ceres might actually have a water cycle. Through studying Julian Crater, a crater that has very steep walls, Ceres noticed that the ice on the bottom of the crater was accumulating differently during periods of summertime. So in Ceres summer, the sun rays would be hitting the bottom of the crater, possibly sublimating the ice and causing it to condense on the steep crater walls that never actually see sunlight. Alternative explanation, a little more mundane, there's mini rock slides that are uncovering subsurface ice. So, tantalizing, but we don't know for sure yet. As Ceres ran out of fuel, it inserted into its lowest orbit yet, a mere 30 miles or 50 kilometers above the surface of Ceres. This allowed for absolutely stunning photographs, but also for new science in the form of analyzing the surface using gamma rays and spectra data. Some of the stunning photographs of the low orbit included more views of the famous, or rather infamous, bright spots of sodium carbonate that people theorized were alien moon bases or whatnot when they were first discovered. So, but we got plenty of eye candy of the spots and other views of Ocator Crater as Ceres descended. That's pretty nice. Real nice. Looks like Earth. That's cool.
That's cool.
But all good things come to an end. Ceres did not check in with NASA on the 30th of October, as of or on the 31st, and on November 1st, NASA announced that Dawn had run out of hydrazine and could no longer keep pointing at Earth to transmit data back home, therefore was declared dead. But the data is still coming in, and one of the things that is being analyzed even last month was based on that spectra data of its low orbital dive. There's a lot of organic material on Ceres. Dr. Simone Markey from the Southwest Research Institute referred to Ceres as a chemical factory. It has several times the concentration of carbon that is found on the most carbon-rich primitive meteorites that have fallen to Earth. So consequently, Ceres could be a very, very interesting place. But that's the end of Dawn. Then we've got Kepler, the great planet hunter, was also running out of fuel simultaneous to Ceres. Now, in May it embarked on its 18th observing campaign, focusing on the Beehive star cluster and the rather infamous asteroid Apophis, one of those doom asteroids that is not actually going to hit the Earth. It actually looked at these back in its early mission, 2005, it was its 5th orbit, and was now revisiting it, collecting new views, new data, and generally expanding our view of things. So, Kepler, of course, had a rocky history. It lost not one but 2 reaction wheels and also dealt with cosmic ray blasts. For most of its lifespan, it was actually in the K2 phase of its mission because the original Kepler objective of a super tight focus on a small area of the sky was hindered by the failure of the reaction wheels fairly early on in the mission. But despite that, it was able to complete 17 observing sessions and was in fact in the 18th, at which point it became clear that the fuel reserves were running pretty low. One of the stories that broke last year, I'm not going to get into it too much, but it caught in the act a fast-evolving luminous transient, or FELT, the kind of thing that I'm sure Dave Bailey would be interested to tell us about, a very rare event of a supernova that instead of persisting for weeks or months, fades in a space of days. So, Kepler was the first craft to actually catch one of these in the act, and so hopefully there's more to come on that story. But Kepler ran out of time the same exact week as the Dawn mission. On the 30th of October, NASA announced it was out of fuel, which soon be shut down completely. In the course of its mission, it found more than 2,600 confirmed exoplanets, many more candidates that have yet to be confirmed. In fact, Kepler accounts for about 70% of the exoplanets known today. It was the little probe that could. Fortunately for exoplanet enthusiasts, TESS, the transiting transiting exoplanet survey satellite, is already up there. It launched in April. It's been placed into a highly elliptical orbit that transmits data every 13.6 or 13.7 days. And TESS lost no time in snapping its test image, so on May 19th it was already going. Very pretty. It had a whole batch of exoplanet candidates that had already been prepared for it by K2. So the Kepler mission really did pave the way for TESS, providing it with, hey, look here. So TESS could get up and running very quickly. And in fact, started science operations in July. And that is its first light science image of the southern sky. That was September. And by 20th of September, we had 2 planets already. One of them is around a star called Pi Mensae in the constellation Mensae. It's about 60 light years away from Earth. It is a naked eye star that was previously known to have a planet 10 times the size of Jupiter orbiting it. Well, this is more like a hot Neptune. So TESS is up and running, and we heard today that it's got a 3rd planet candidate confirmed. So exit Kepler, enter TESS, we're good.
Thank you very much. Okay, we're gonna go a little bit over tonight, not too long though, but we're gonna go a little bit over. Jerry, come on up and give us an update on LIGO, and then I'll give a very, very brief summation of the stories that didn't make the top several. So there you go. Go for it.
Well, good evening, everybody. So back in November of 2017, I gave a talk to this group on the discovery of gravitational waves by 2 different gravitational wave detecting systems. One was LIGO, or Advanced LIGO, and the other was Advanced Virgo. LIGO's in the US and Virgo's in Italy. At the time I gave my talk, there were 7 events which had been detected. 6 of them were due to the merger of black holes and binary systems, and the 7th one turned out to be a collision of 2 neutron stars, also in a binary orbit. During 2018, no additional measurements were made because both of these systems were shut down to work in enhancing the sensitivity of the facilities so they'd be able to survey a larger volume of space in the future. So, within the last month or so, even though no new observations were made, analysis of old data using improved mathematical algorithms has shown that there are 4 more gravitational wave events which can be confirmed. And so what is shown here are now the 10 black hole mergers which have been determined. And so the original data are these, plus this one down here. And the new data, new gravitational waves are here, here, there, and this. So again, these are due to black holes which are in orbit around each other, emitting gravitational waves and spiraling closer and closer together, and eventually colliding and merging into a single black hole. So the spectra that you see here is only over about the last 1/4 of a second of the lifetime of these spiraling black holes. This is another way of showing the same kind of data. Here you see the gravitational wave oscillations. And over here, gravitational wave oscillations. On the left, you see another way of displaying the data in which they are indicating the frequency of the gravitational waves. As the black holes spiral closer together, they go faster and faster. And you can see the frequency increases until it's suddenly cut off at the merger. And so here we have frequency as a function of time, and this turns out to be a logarithmic scale for that display. So by using Albert Einstein's general theory of relativity, one can analyze the gravitational wave data and determine the masses of the black holes, both before they collide and also the mass of the black hole after they collide and coalesce into a single object. And so what we have here are the masses displayed. What you see are 2 orbiting black holes which merge into this one, these 2 merge into that one, and so forth. And indicated here are the masses in terms of the mass of our own sun. So for example, in the first case, we have a black hole with about 20 solar masses merging with one with about 30 solar masses, producing a new one with a mass of about 50 solar masses. So looking at the display of masses here, we see that the most massive one is approximately 80 times the mass of our sun, and the smallest one detected are the order of 7 solar masses. So looking into the future, the plans now are for advanced LIGO and advanced Virgo to have the upgrades completed and to come back into operation sometime in the spring of 2019. They'll start the third run, known as Observing Run 03. It's expected to last for about a year, and during that time, with the new sensitivity, they're expecting to see tens of gravitational wave signals during that year's time. And towards the end of that run, there's a Japanese detector known as KAGRA, which is expected to come online. And with more observing sites on Earth, it's possible to determine more precisely the location of the events which produce these gravitational waves. Okay, thank you.
Okay. Thank you, Jerry. Okay, I'm going to briefly run over some of the quick stories that we had. Actually, from the time we started, we're at 58 minutes, so we've done pretty well. The important stories of the year: John Young, the most experienced of the U.S. astronauts, he died at 87 years old out of Houston of pneumonia, and he walked on the moon in 1972 and even smuggled a corned beef sandwich there, by the way. He went to space 6 times. We lost Stephen Hawking, which is probably one of the biggest stories of the year. He died on Pi Day, 314, and was a world-renowned, of course, physicist, cosmologist, and so on and so forth. And he made a large impact on astronomy, certainly. And we lost Alan Bean on May 30th, who was the Apollo moonwalker and died at 86 years old. He was an Apollo and a Skylab astronaut, the 4th human to walk on the moon. Died at 86 in Houston. We had a meteor, if you recall that came down near us. And there's a little quick picture of that. Give you an idea of what it looked like. We'll do another one. That's how it lit up the sky. And this one is from a door cam, actually, that shows you how bright it was. And many went out to try and get pieces of it. A little bit more on the Oumuamua, which was a interstellar asteroid. And what we've discovered from that, actually, in the last few views, was in fact that it was a comet. So it showed when it got by the sun that it got a tail and all the nice things that went with it. It probably came from a binary star system, is the study. And of course, like I said, we found out it was a comet. And to move along, Planet 9 became something in the astronomers point to new evidence that there's some perturbations and things that are going on in the Oort cloud, and it seems that there's an object of great mass, or a group of objects, they're really not sure yet, a group of objects out there that is influencing the others. Of course, we do not have the telescope capability to view this, but it could be a Neptune-sized object or just a whole mass of stuff.
You know what created that? When we demoted Pluto,
Again,
it had to be replaced.
of course. Again, this is a little bit more about that. Collective gravity, not Planet 9, may explain the orbits of the detached objects, is what they've discovered from that. We found an extreme distant solar object, found the most extreme, and it was 2015 TG387 by the Carnegie Group. The first interstellar immigrant discovered in the solar system. There were other asteroids that came through that we're discovering also. They find new evidence of complex organic molecules from Enceladus, which is the moon that goes around Saturn, and it spews water out. We also, during this last year, found that there was ice confirmed on the moon's poles, our moon. There's ice. We also found that Mercury's chemistry is very strange, and we won't get into the details of that because we don't have time to do that. And of course, we did find a lot of new material about it. It's very cold where that is. It's shadowed areas that have a negative 170 degrees Celsius. Pluto's weird ridges may be glacial landforms unlike any on Earth, which is a study from the New Horizons. And of course, the brightest comet of the year was in November. It was 2018. It was Comet 46P Bertin, and you could see it with binoculars. And a little bit more on that, and that's it. Those are the stories that didn't make the top, but I was able to do that in 2 minutes, so that's pretty good. And thank you very much for all that you
Do my job, Jonathan, just go.
Questions at the Coney? After the meeting, we go to the Coney on 12 Mile. If you have any more questions about this, whatever presenters that attend that, you can ask them there. That's pretty much it for tonight. We'll see you at the eclipse on Sunday.
Make sure that you see Dale Partin in my presentations. They should probably be extraordinarily interesting, certainly Dale's.
Please take snacks on your way out the door.
Yes, take whatever you like.
Except for that cell phone, which probably
Don't take my cell phone.
Well, can't eat the cell phone.
Don't eat my cell phone. No, I think just what comes in that one.
Yeah, yeah.
And then the over.